Good afternoon, Professor Wang and also Professor Wang. Ladies and gentlemen, welcome to this pair distinguished lecture. My name is Qingyan Chen, the Director of Purdue Academy for Interdisciplinary Research, or PAIR. So today we are very pleased to have our distinguished speaker, Professor Wang, Regents Professor in Chemical Engineering at Washington State University in the United States, to be with us. So dedicated to bring the sustainable technology for energy and environmental applications, Professor Wang focused on the development of novel catalytic materials and reaction engineering for converting carbon sources, including fossil, biomass, carbon dioxide, and plastic waste into sustainable fuels and chemicals. His research team at Washington State works closely with the Pacific Northwest National Lab, or we call PANS, panel, sorry, where he served as the acting director of the Institute for Integrated Catalyst. Is in understanding catalyst and catalysis process at the atomic or molecular level. Professor Wang's expertise spans from fundamental principles to crucial industrial applications. His discoveries and innovations culminated into a range of practical technologies to pave the way for a clean future. Professor Wang holds 287 patents, including 111 issued US patents. And among those patents, 90% has been licensed to industry. It's a very remarkable achievement. Professor Wang's excellence in research and technology transfer is widely recognized. He has received prestigious honors, including the 2025 Wilhelm Award in Chemical Reaction Engineering by the American Institute of Chemical Engineers, and the 2025 Robert Burwell Lectureship in Catalysis by the North American Catalysis Society. And he is also a member of many prestigious academies and associations, including the National Academy of Engineering in the USA and the National Academy of Inventors in the United States. So he also published in Nature. So you can see his research really span the whole trend, from the fundamental research to the applications. So today we are very happy to have him with us. So without further ado, ladies and gentlemen, please join me. Welcome Professor Wang, please.
Well, thank you, Professor Chen, for the introduction. And also, I really appreciate Professor Chen for the very kind invitation to give me the opportunities to share with you about some of the recent progress in the energy and the environmental area. PolyU has always been the university that I admire very much. This is my first time visiting this university. You are very recognized in innovation and applied research. Even the moment when I first stepped into the campus, when I saw Jockey Club Innovation Tower, it actually reminds me whether I'm actually walking into the campus or a futuristic place, like almost like onto a movie, like a science fiction movie set. So that speaks how unique this campus is. And in my presentation, I will try to make some effort to show the industrial and the application relevance of our research, to at least show some relevance with what this university values. And at least I hope I will be able to keep you awake before dinner. So for those of you who are not familiar with the Washington State University, it's in the northwest corner of the state of Washington. And don't be confused with Washington, D.C., which is on the completely opposite, another side of the United States. And also, don't be confused with Seattle. Seattle is very recognized city in the state of Washington. It's on the Evergreen side. And the Washington State University and the Pineal are located on the eastern side of state of Washington. We call it Evergreen State. And the university itself is surrounded by the wheat fields, okay? And occasionally, depending on the season, you could see very green, like especially in the spring. And the university is a land-grant university established in 1890 with 11 colleges, 31,000 students, about 2,400 faculty members. And we're extremely happy to see our chemical engineering program, at least for the past 2 years, have been consistently ranked at a number 13th in the country. I don't know how much we should pay attention to the rankings, but in my opinion, it's better to be listed than not being listed, because when I joined the Washington State University back to 2009, we were not on the list, because if you are outside of top 75, you are not listed. So it's good to see our ChemE program consistently climb the ranking in the list. Pacific Northwest National Laboratory, on the other hand, is one of the 17 Department of Energy's national laboratories in the US. And it was established in 1965 as a part of the effort to clean up the nuclear waste, which was generated during World War II as part of the Manhattan Project, which has produced the plutonium for one of the bombs dropped in Japan. So when I first joined the laboratory 31 years ago, the entire laboratory was focused on nuclear waste cleanup. Now we have 90% effort devoted to science, energy, and also national security. The laboratory now has about 6,500 staff members with the research expenditures of about $1.5 billion. In the Catalysis Institute, we have about 120 scientists, not including postdoc and visitors, okay? So today's talk, I want to share with you about what catalysis is doing in today's energy and environmental space. I don't think I need to convince everyone here that catalysis has played a vital role in converting all the cheap resources, including coal, oil, and natural gas, to value-added chemicals and fuels. And if you look at the global GDPs, catalysis is contributing about 30 to 40%. So it's extremely important. And also, if we look at how the chemical plants look like today versus the first chemical plant, back to the first plant, which was established in 1831 for the chlorine production in Scotland. Very dirty, very inefficient, to what it looks like today in terms of a cleaner and a more energy efficient chemical plants. Catalysis has played important roles. So if you look at the definition of a catalysis, it's very simple. It's essentially the process that you can accelerate a chemical reaction by introducing catalysts, which will lower activation energy barrier. So the reactants can be converted to products very efficiently with less energy input. Okay, that's textbook definition, but I personally like Chinese definition of catalysis much better. We call it matchmaker, okay? So a good catalyst will rapidly bring couples together, okay? We call it activity. And of course, it has to be the right relationship, so it can last, forever. So we call it selectivity. And of course, matchmaker, once the relationship is established, matchmaker needs to work on the next couple. That's called catalyst cannot be consumed. And of course, matchmaker needs to do this process again and again. That's called catalyst stability. So I personally like Chinese definition of catalysis better than the textbook definition. And if we look back the history, perhaps the most impactful contribution of catalysis is ammonia synthesis. which was invented by Fischer-Tropsch and Carl Bosch. Fischer-Tropsch actually won Nobel Prize back to 1918 for discovering this process. And Carl Bosch won the Nobel Prize in 1931 for commercializing this process. And this process is very critical in producing ammonia from nitrogen and hydrogen, which increases agricultural production rate tremendously. For example, the corn production increased by at least 6 times with this process. And if you look at the total population in the world, half of the world's population would stop without invention of this process. And today, I want to share 2 recent progresses in our research. One is related to energy space. Another one is related to environmental, okay? And the first one is related to the Fischer-Tropsch synthesis, which was discovered by Franz Fischer and Hans Tropsch back to about 110 years ago. And this process was commercialized about 100 years ago, okay? It's essentially the process converting a mixture of carbon monoxide and hydrogen, which is called a syngas, and it can be readily obtained from carbon sources, including biomass, coal, and natural gas. And this process is able to build up the carbon chain length of hydrocarbons for the aviation fuels, marine fuels, or even liquid fuels for personal passenger cars or trucks. Even though this process has been commercialized for about 100 years, but there are still a lot of fundamental questions remain unaddressed, including how the chain growth actually happens, whether it's because of the coupling of CHX units or because of the CO insertion into the intermediates. So those questions still remain unanswered, okay? And of course, you can imagine for the complex reactions like Fischer-Tropsch synthesis, they are operated at far away from equilibrium. They are highly nonlinear, and also multi-state system actually may present. So you may see different steady states in which will be reflected by, for example, the hysteresis, oscillations, all the crazy catalyst behaviors, okay? And such so-called dissipative structures was first discovered by Prigogine, who won the Nobel Prize because of this discovery. And of course, the classic example is really reflected by a homogeneous reaction system. We call it Belousov and Zebzinski solution or reaction. What it does is, if you mix serum cations, 3+, for example, with acids and borates, serum 3+ will constantly be oxidized by borates to serum 4+. And the presence of monoic acid will constantly reduce the serum 4+ to 3+, because the serum 4+ is yellow color and the serum 3+ is colorless. So this constant reduction and oxidation will result in the oxidation of these colors. It's almost like a cocktails. And in the heterogeneous catalysis area, the CO oxidation, in terms of oxidation, of CO oxidation, was first reported by Wick. And Erdl demonstrated this experimentally using platinum single crystal. And Erdl won the Nobel Prize in 2007. Of course, in the complex chemical reaction systems, because you have to talk about mass and heat transfers within catalyst bed and also in the reactor, those oscillation behaviors are typically masked, so you wouldn't be able to observe experimentally. But in the Fischer-Tropsch synthesis area, which is a very complex reaction, we have been very lucky with a very talented student who actually observed this oscillation even in the chemistry, which has been practiced for 100 years. And this is demonstrated on a cerium cobalt Fischer-Tropsch synthesis catalyst with an atomic ratio of a 2-to-1 ratio. And this catalyst can be readily prepared in oxalic acid by co-precipitating the nitrate precursors, okay? So what we will see is the moment you turn on the reaction, under typical Fischer-Tropsch synthesis conditions, 220 degrees C, and the hydrogen to CO ratio of 1-to-1, you will see oscillation, okay, of temperatures, and you see it actually oscillates every 340 seconds with amplitudes of about 7 degrees Celsius. And so this oscillation is real, okay? And you can also look at the oscillations under various hydrogen to CO ratios from 1:1 all the way to 6:1. And if you look at the temperature, if you look at products and the reactants, they all oscillate. And more importantly, the products actually are completely out of phase with the reactants, as illustrated in this plot. And all the conversion behaviors for these reactions at various hydrogen to CO ratio resembles typical Fischer-Tropsch synthesis process. Like, for example, when you increase hydrogen to CO ratio, you will see the increase in conversions. That's because the Fischer-Tropsch synthesis reaction is a first order with respect to hydrogen partial pressure. And also you do see increased methane selectivity as you increase the hydrogen to CO ratio. That's well documented in the Fischer-Tropsch synthesis area, okay? And more importantly, if you plot phase space trajectory as a function of hydrogen to CO ratio, what you see is a clockwise hysteresis at a various hydrogen to CO ratio. And you have to keep in mind, Fischer-Tropsch synthesis is a highly exothermic reactions. So this really demonstrates this reaction has chemical kinetic origins. That's because as the reaction rate goes up, more heat of reaction is generated. So the catalyst surface will become hotter. And the reactants absorption on the catalyst surface will decrease. And the decreased absorption of reactants will result in the reduced coverage of reactants and leading to reduced reaction rate. And once the reaction rate is reduced, the catalyst surface temperature will drop, and which will lead to the enhanced absorption of reactants, so the reaction rate will increase again. This is why you see this clockwise hysteresis. And more importantly, if you look at how the products are formed, okay, the moment you turn on the reaction, what you see is methane is formed immediately, followed by carbon dioxide and water. This actually resembles the mechanism I mentioned earlier, the CO insertion mechanism. In this CO insertion mechanism, what you will see is the methane will be formed immediately, followed by water and the CO2. That's exactly what we saw experimentally. So with this insight, our theory collaborator, Paris Gaspard, simulated this process. What he predicted is exactly identical to what we observed experimentally in terms of temperature, reactant oscillation, and also product oscillations. So you may ask how important this discovery in the oscillation is to the practical applications. After we published this paper, our friends back to ExxonMobil told us this actually explains why they always observe much better product yield during the night operation when the process has less interference by human operations. So essentially what it tells is even for the chemistry, which has been commercialized for 100 years, you can still identify what the most reactive states of a catalyst will be and try to take advantage of that identified reactive states and maximize product yields in the operation, okay? Now, next example I want to share is the recent work in environmental application to enable the more efficient power generation from internal combustion of fuel supply chains, okay? And this is probably the second most impactful I think the practice from catalysis. This is essentially showing the difference in Los Angeles before Clean Air Act was implemented in 1970 and after. Okay, you can see tremendous difference in the climate impact. Okay, this act essentially requires all the emissions from stationary and also mobile sources are regulated, which is implemented by a catalytic converter, essentially converts the hydrocarbons, nitrogen oxides, and the CO to water, CO2, and the nitrogen, so you can emit to the air without harming personal, human health. Okay, and of course, if you look at the catalyst utilized or metal utilized for this process, many they are implemented by platinum group metals, and that's the primary reason you see about 80% of palladium and rhodium are utilized, and even about 40% of platinum are utilized. And it's not surprising. The stricter environmental regulations, doesn't matter whether you are looking at the places like Europe or US, because of stricter environmental regulations, what you see is an increased usage of platinum group metals to meet the current and the future regulations, okay? And this is the primary reason you see the increased platinum group metal costs and also shortage in the supply. Some of you may recall 2 years ago, rhodium price increased to as high as $60,000 US per troy ounce. Even today, it is still very expensive, costs about $6,000 US per troy ounce. And this issue is not going to get alleviated. That's really because if you look at ExxonMobil's projection in energy usage, it's predicted to have at least 25% increase in energy usage for the next 20 years, and especially in the area which are more difficult by batteries, for example, rail, aviations, and marines. And that's really because of increased personal buying powers and increased economic activity, which drives the transport of goods and the service by those sectors. And another part we also have to also keep in mind, as we transition from a fossil-based fuels to renewable-based fuels, for example, ethanols, biodiesels, or even hydrogen or ammonia, there are a lot of uncertainties related to how do you implement those internal combustion process using variety of the fuels. For example, if you use hydrogen, the product is water, so there will be about at least 20% of water content in the exhaust. And you have to worry about the durability of catalysts under high water content, not even mentioning unburned, for example, hydrogen, which could reduce catalysts and lead to different deactivation. When you use ammonia, for example, as a fuel for the internal combustion, you will generate hundreds times more nitrogen oxides emissions. And that means you have to use more platinum group metals in order to meet the same requirement. And this list goes on, again and again, okay? Of course, ideally, if every atom of platinum group metals can be utilized, this could be one way to reduce our dependence on the platinum group metals. And of course, if you look at the literature in terms of the ways to make so-called single atom catalyst. Single atom catalyst by definition is every metal atom is accessible for the catalysis. There are a variety of ways to synthesize single atom catalysts, including you purposely increase the defect size of the supports, so every metal can be dispersed at a high density, or by so-called strong electrostatic absorption, so you make catalysts highly dispersed at a precursor stage. Or you use the confinement, for example, using zeolite, MOPS, COPS, those microporous supports to confine single atoms to stabilize them. But in the application we're interested, there are dual challenges, okay? If you look at the CAFE standards, it requires all the vehicles, doesn't matter whether you are talking about personal passenger cars or trucks, they have to be more and more efficient. That means there will be less energy in the exhaust. And at the same time, the environmental regulation, the current regulation requires all the emissions, hydrocarbons, nitrogen oxides, and the CO, they have to be kept at 30 milligrams per mile driven, okay? And this standard is going to become even more stringent in 2032. Essentially will be cut into half. You have to meet like 15 milligrams. Now, how challenging that it is. If you look at the moment when you started the car, if you look at the exhaust temperature and also exhaust, even before the exhaust temperature reaches 150 degrees C. If you don't do anything to convert those criteria emissions, you already exceeded the limit of environmental regulation. That means you have to do something to make a catalyst very reactive at the temperatures below 150 degrees C. This is what DOE defines as the 150 challenge, requiring all the criteria emissions be converted at 90% at the temperatures below 150 degrees C. So to make a catalyst reactive at a low temperature is already very challenging, but you have to keep in mind, eventually exhaust temperature will get hot, especially under high engine load or under periodic filter regeneration. The temperature could go as high as 1000 degrees Celsius. So that means catalyst not only has to be stable at a very high temperature, but also has to be very reactive at the temperatures below 150 degrees C. This is the dual challenges we're facing in those applications. And how crazy that is. So let's just give one example. If you take a conventional diesel oxidation catalyst, which is platinum supported on alumina, the fresh catalyst is highly dispersed with a 1 to 3 nanometer particle size. But by exposing this catalyst, even at 800 degrees C in air for just 10 hours, you will see the sintering of those nanoparticles from several nanometers to micron size, size. So it's almost 3 orders of magnitude increase in the particle size. That means the dispersion will decrease by 3 orders of magnitudes, and the catalyst activity will decrease by also 3 orders of magnitudes. So this is just one example showing the potential catalyst deactivation because of sintering. And of course, at high temperatures, you also have to worry about the potential deactivation because of the solid state reactions between metals and also support, which will also deactivate catalysts. And some platinum group of metals, for example, platinum, under those conditions are quite volatile. So you could also lose some of those metals under those conditions. So in our work, we focus on 2 approaches to stabilize platinum group metal single atoms. And one approach is we call it nano island confinement of single atoms. This is really based on the fact that all the metal oxide surface at a different pH, they have a different surface charge. And every metal oxide has a point of 0 charge, which means at a particular pH, the surface will be neutral. Below that pH, the surface will be positive charge, and higher than PZC, point of 0 charge, the surface will be negative charge. So this concept essentially is to take this advantage of different surface charge. Like for example, you start with a silica, okay, which has a point of 0 charge of 2 pH. And if you keep pH above 2, the silica surface will be negative charge. And when you introduce, for example, cereal precursors, which is a positive charge, will be selectively, dropped, deposited on the silica surface because of the strong electrostatic absorption. And of course, you can control this process by controlling the concentration and growth time, so you can control the serial nanoparticle size from 1 to 2 nanometer size to even up to 10 nanometer size. And after you grow those nanoparticles or clusters of cereal on silica, now you can take advantage of the different point of 0 charge between silica and the cereal, because the silica has point of 0 charge of 2, and the cereal has 6. If you choose a pH in between, then silica surface will be negative charge, and the cereal surface will be positive charge. And if you take, for example, platinum precursors, which is negative charge, then platinum precursor will be selectively deposited on cereal because of the negative and the positive charge situation. By doing this way, you can precisely control how many atoms you want deposited on each cluster of nano island. And of course, because platinum has much stronger interaction with the cereal as opposed to the interaction with the silica, even under oxidative or reductive conditions, or even high temperatures, those platinum atoms would be confined in each island because the energy for the atom to jump from one island to another will be much higher. And this is exactly what we saw. If you use a CO and the IR, essentially looking at the CO vibration with IR measurement, it actually tells you the identity of a platinum. For example, the freshly synthesized samples has this characteristic band, which is a CO vibration representing of platinum cations. And after reducing those cations, and those platinum are still atomically dispersed. So you don't see the centering of platinum. So otherwise, you will see the signatures in the higher wave numbers show up in the CO IR measurement. And of course, if you use this approach, you use CO oxidation as a probe reaction, essentially measuring the CO oxidation as a function of light-off temperature. The freshly synthesized catalyst doesn't have much activity, but after you reduce it, it actually increases activity by shifting light-off curves to achieving like about 100% conversions at about 150 degrees C. And you can repeat this process again and again, and the catalyst is very stable. This is just illustrate by confining single atoms on each island or each nanoparticle size, you can stabilize single atoms under oxidative reductive conditions, even at high temperatures, okay? So this is one approach. The second approach, we call it atom trapping, and this is really based on the fact that all the transition metal and the metal oxides, they have some volatilities at high temperatures. So let's just take a platinum as example. If you heat up a platinum in air at 800 degrees C, you will oxidize platinum to PtO2. PtO2 is very volatile, has the vapor pressures of 10 to minus 8 atmosphere. So you may ask how significant those vapor pressure is. If you assume, okay, each molecule in the gas phase collide with the surface once and stick on the surface, it only takes 1 second at the pressure of 10 to minus 9 to form a monolayer coverage on the surface. So when you have the situation that the vapor pressure is 10 times higher, you can imagine this process is very efficient in forming like a surface coverage by the gas phase molecules, okay? And this is exactly what we demonstrated about 9 years ago in collaboration with Abaya Datia from University New Mexico and also CEO from General Motors. So what we demonstrated is if you heat up supportive platinum precursors, if there's any support with the defect sites, for example, Syria, the volatilized PtO2 will be trapped by the defect sites of silver oxide and to form square planar type structures because the Syria 3+ in the steps edge sites will be able to reduce gas phase PtO2 and form PT2+, and with this square planar type structure, very stable on the step edge sites, okay? So this is another example showing how the thermally stable single atoms can be synthesized because by default, those materials are synthesized at 800 degrees C in air, so they are very stable. So in the rest of my presentation, I will share some examples we call it unconventional way to activate those catalysts because as you can imagine, those catalysts synthesized by those methods like atom trapping, they are fully coordinated, so they shouldn't have any activity or not much activity. So what we have been able to demonstrate is by unconventional way to activate those catalysts, which mimic the conditions in the exhaust. For example, high temperature, high water content, or sometimes even unburned CO and the nitrogen oxides. How do we turn those catalysts into very reactive catalysts? And we call it unconventional pretreatment to increase catalyst activity, okay? So this is just one example showing the CO oxidation light-off curve. If you just take a platinum single atom catalyst prepared by atom trapping, essentially by heating samples to 800 degrees C in the presence of air, and you measure the CO oxidation as a function of light-off curve, and this is a very lousy catalyst, okay? And the platinum, as illustrated by the stem here, are atomically dispersed, And you don't see the 100% conversion of CO until about 325 degrees C, way below the 150 requirement. But to our surprise, if you treated this catalyst at 750 degrees C in the presence of 10% of steam, that's the typical hydrothermal agent conditions required by auto industries before they trust any performance. All of a sudden, we see the activity is increased tremendously as illustrated by the shift of light-off curve. Now you see the catalyst activity reaches 100% conversion at 150 C. This is very much counterintuitive because normally you would expect when you expose materials to high temperatures in the presence of steam, the material will center and the performance will decrease. But in this case, what we saw was completely opposite behavior. And it took us quite a while to figure out what happened. Of course, if you look at the stems, even after hydrothermal aging, platinum still atomically dispersed. What happened is, under those conditions, a high temperature, 750 degrees C, in the presence of water, the oxygen vacancy will migrate from the bulk, to the surface. And in the presence of water, water can dissociate and form hydroxyls. And those hydroxyls in the close proximity of single atoms of platinum, they are opening alternative reaction pathways. So when CO is introduced, it actually reacts with the CO to form formate. And this formate can be rapidly decomposed to form CO2. And this reaction pathway actually has much lower energy barrier compared with the case without hydroxyls, where the oxygen activation step has very high barrier, 122 kilojoules per mole. Okay, so after our report on this unusual behavior by hydrothermal aging, you see a lot of publications in this area. By just doing high temperature steam treatment, you see the tremendous increased activity, not only in CO oxidation, but also in three-way catalysis, formaldehyde oxidation, or even methane oxidation. So this behavior now is widely practiced in the field to increase catalyst activity. Now, besides platinum, which will form square planar, stable structure, and if you look at palladium, it also has a similar type of behaviors. If you heat up a palladium and also support at high temperatures, and the palladium will also form stable single atoms, just like a platinum, as opposed to the energy required to form palladium nanoparticles. Now, why we're interested in palladium? That's really because of the potential application in natural gas powered vehicles, because the natural gas powered engines are 20% more efficient than gasoline or diesel engines. And it's projected to have about 30 to 40 million vehicles on the road powered by natural gas. However, that's one challenge, that if you cannot completely oxidize and burn the methane in the exhaust, let's just take an example, 500 ppm, for example, methane. If you don't fully oxidize those, and methane is 30 times worse than CO2 in global warming potential, that's easily translated to about 1.2% of CO2 emitted in the air. So essentially, we'll negate all the benefits by running on natural gas powered vehicles. So this is challenging with the engines to use natural gas. If you don't have the control in the emissions, you don't have the potential, practical application for this technology. And if you look at literature, palladium is the best catalyst for methane oxidation at a low temperature, but palladium is also notoriously infamous in terms of deactivation and also the strong interaction with water. So when we first look at this application, we just want to see how the single atoms prepared by atom trapping may perform under those conditions. And to our surprise, the catalyst prepared as is, which is lousy catalyst, you don't see much activity. However, if there's a trace amount of CO in the exhaust, even at the room temperature, it actually can turn this catalyst into very active catalyst, even more reactive than the baseline catalyst palladium on alumina. So what happened? And first we'll look at, again, using CO IR to actually probe what happens to palladium in itself. What happened is at about 190 degrees C reaction temperature, we see palladium is present as single atoms. But as you cool down the temperature, all of a sudden you see the characteristic peaks associated with the palladium nanoclusters show up. That means palladium single atoms at high temperatures, they are atomically dispersed, they are stable. But once you lower the temperature to room temperature, in the presence of trace amount of CO, they center to form clusters. And this can be confirmed by stems. And also you can do another experiment by purposely expose single atom of palladium at room temperature, but by introducing a small amount of CO. The moment you introduce the CO, you see the characteristic peaks of palladium clusters, okay? And you can also do another experiment, Raman, which is essentially looking at the asymmetric stretching vibrations of oxygen ions around serum cations. If there's any change in the serum cation environment by removing oxygen, you will see the peak shift. And essentially what you saw is the moment you introduce the CO, you see the blue shift. That's really because of readily removal of oxygen in the serum cation environment, okay? And you can also look at in situ XFs and to confirm what happened to the palladium. So what we saw is at a room temperature, in the trace amount of CO, what you see is a palladium coordination increases. That's because of the formation of palladium nanoclusters, accompanied by the decrease of palladium oxygen and the palladium serial coordination. Again, that's because the palladium is coordinated with the palladium itself. But once you heat up to high temperature, they redisperse, get back to the original state. And you can also use this theory to confirm what really happened, okay? And the theory essentially is looking at, for example, palladium single atoms on two surfaces. One is at the step edge site, one is on the terrace site. And at a high temperature, like 800 degrees C, without any CO, they are very stable. But the moment at a room temperature, when you introduce trace amount of CO, both becomes less stable. More importantly, the palladium single atoms on the step edge sites are much less stable, so they actually will migrate to the terrace sites and form clusters at a room temperature in the trace amount of CO. This actually provides a tremendous self-healing catalyst. So imagine the moment that you start engine, you start with a single atom catalyst, palladium, which is not active for metal oxidation, but the trace amount of CO generated in the exhaust will turn this catalyst into the cluster, which is very active for low temperature metal oxidation, okay? And as the exhaust temperature increase, those clusters will redisperse, even though activity will decrease, but you got a temperature to compensate for the reduced activity. And you can imagine this actually process can be repeated again and again. Next time when you start an engine, when the exhaust temperature is low, you will get back to the initial state, okay, which is less active for low temperature oxidation, but the moment you generate some CO in the exhaust, this catalyst will be very reactive. So you can repeat this process again and again, okay? And the last example I want to share is rhodium. And if you look at the calculations, rhodium, similar to platinum, will also form stable rhodium coordination with the step edge sites. So just similar to platinum by atom trapping. Now, the reason why interesting in rhodium is because rhodium is the best catalyst for three-way catalyst, essentially to reduce NO by CO. That's widely commercialized and practiced in industries. But in literature, it teaches you need a two adjacent site of rhodium so the nitrogen can be formed. That's why in practical applications, you have to use rhodium nanoparticles. But under those exhaust conditions, those small nanoparticles will grow and form larger particles, or even form alloy with other metals, and which leads to the deactivation. So in practical applications, industries or suppliers always use excess rhodium to make sure catalysts, even towards the full useful life, they still maintain a certain reactivity. So that's why a lot of rhodium are utilized in catalytic converter. So in our case, when we use the atom trapping to prepare those catalysts, we can confirm rhodium is atomically dispersed by TEM and also by COIR. So rhodium is present as dicarbonaceous rhodium 3+. But more importantly, when we look at the activity of NO reduction by CO, the rhodium single atoms prepared by atom trapping is very reactive. I mean, it reaches 90% conversions at about 100 degrees C, so much more reactive than what literature reported. And if we look at CO and also NO experiments, what we saw is the moment you introduce NO, the rhodium actually is oxidized from rhodium 1+ to rhodium 3+. And also you see the hypernitride formation accompanied by the N2O formation. This is exactly what homogeneous catalysis community reported about 50 years ago. So they essentially reported mononuclear rhodium 1+ or 3+ are very reactive for NO reduction by CO. And the rhodium 3+ is present when NO is introduced and reduced to 1+ when CO is introduced. And the reaction mechanism has zero order with respect to CO and NO, and also is first order with respect to rhodium. And this is exactly what we saw with the single atom catalyst prepared of atom trapping. So there are common analogies between homogeneous and heterogeneous catalysis. And 4 years ago, actually 5 years ago, we actually formed a team with industries and also universities and responded to DOE open call for proposals. And we thought this would be very straightforward to translate what we have seen so far with the rhodium to industrial practical catalysts. But unfortunately, what we saw is, regardless of what we did, whenever we use a practical support, the catalyst performance, which is reflected by the temperature required to reach 50 or 90% conversion compared with the baseline, okay? If they are identical, they should, in the same horizontal line. But if they are much worse, they will be above the baseline catalyst. So regardless of what we did, we always see the practical support will give much worse performance than what we saw from the model catalyst, preparation. And if we look at it more carefully, if you take alumina supported cereal, the commercial support used in the vehicles these days, and when you put rhodium on and did atom trapping, what you see is rhodium is not only trapped by cereal, but are also atomically dispersed on alumina. And those rhodium sitting on the top surface of alumina, they are much reactive, much less reactive. So essentially are wasting a lot of rhodium for not doing reaction, okay? And we actually, again, completely stumbled into this discovery recently that what we discovered is at a high temperature, like for example, 980 or 800 degrees C, when you do the hydrothermal aging, if you introduce trace amount of NO or NO2 or N2O, even at 450 ppm, that's very representative to the exhaust. What it would do is actually will redisperse cereal to atomically dispersed cereal. Okay, this is essentially showing if you just age in this catalyst, okay, aluminum supported cereal under hydrothermal aging conditions, what you see is just, cereal nanoparticles, but in the trace amount of NOx, those cereal will be redispersed into atomically dispersed cerium, and those are very reactive for any oxidations involving oxygen. And to quickly, demonstrate the end results is if you take this catalyst and the fresh catalyst, this is the NO level in the exhaust. This is a baseline. If you do hydrothermal aging, just using steam and high temperature, the catalyst activity will decrease. But in the trace amount of nitrogen oxides, all of a sudden is what actually makes this catalyst much more reactive. Essentially, we discovered a way to highly disperse cereal to make rhodium on alumina much more reactive for this reaction. And this also answered one of the long remaining question in industries, because when you look at fresh catalyst using the catalytic converter, it has a 3 to 5 nanometer size, rhodium particle size. Towards the end of useful life, like 100,000 miles, they grow into 50 to 100 nanometer size particles. So you would expect at least 10 times decrease of catalyst activity. But normally you only see 3 to 4 times. That's really because under those actual operations, lean and rich conditions, they accidentally redisperse the cereal and making rhodium much more reactive. But they were not aware this behavior. Now you can actually proactively pre-treat those catalysts to make them much more reactive at the very beginning in the fresh state of catalyst with a reduced rhodium content. And recently, just a couple of months ago, we actually worked with the industries and demonstrated this in the actual catalyst, which is about 5 inches by 5 inches dimensions. And we compared, the baseline catalyst, which has 2 times more rhodium. And in the engine test, essentially we demonstrated under 2 different numbers, perturbation. So essentially, how much excess hydrogen or oxygen you want to introduce, and also look at CO, total hydrocarbons, and also NOx conversion, and compare both cases. So essentially demonstrated the same performance can be demonstrated with 50% less rhodium. So if we look at North America sector alone, it sells about 14 to 17 million vehicles every year. And each vehicle uses about $350 to $800 rhodium. If you can cut that price by 50%, you can do a simple math, how much will save. So with that, I just want to quickly conclude. Hopefully I shared with you about even the 100-year-old chemistry, very complex. There's still so much for us to learn and provide understanding about the reactive states and to make most of it to maximize product yields. And also, hopefully I also shared several examples and illustrating how in the area to enable energy and the fuel supply chains for power generation using a variety of fuels. What are the innovations we can do to reduce the platinum group metal usage and make an economic impact? And with that, I want to thank my group at Washington State University and my colleagues at PNL, and also my long-term collaborator, Professor Abaya Datia, at the University of New Mexico, and also my collaborators, as well. And more importantly, the financial support by the U.S. Department of Energy. And with that, I want to thank you for your attention, and I'd be happy to answer any question you may have. Thank you.
Okay, thank you very much, Professor Yong Wang, for the wonderful talk. My name is Lianzhou Wang, a professor at ABCT of PolyU, and Professor Chen asked me to chair this session because my research is relevant to Professor Yong Wang's talk. Personally, I learned a lot. Congratulations for the wonderful achievement. So, and we are now actually, the floor is open for some questions. And but before we take the question from our audience here, and we already collected a number of questions from our registered attendance, and I may start with that one. Is that okay?
Yeah. You should share with me earlier.
Yeah. Sorry, and keep it a secret. So, and we have quite a number of questions, and we pick up a few from different group. Like, for example, the first one is from a PolyU staff, and the first question, I just read the question roughly. Given the growing interest in sustainability and when the technology for converting food waste, agriculture residues, like the straw and the crumbs, and into the fuel, and which might become environment economically viable. That means at a large scale.
Yeah. I think this question.
I also see it here.
This is not a new question.
No.
Right. This actually has bothered our community for the past 20 years. is really how do you take renewable carbon sources, like for example, biomass, especially cheap ones, to fuse. I think there are several issues, right? That is still remain unaddressed. One is the scale. I mean, every time when you try to get into fuel space, scale is very important. If you can't actually get up to the scale that is compatible or even closer to petroleum-based, I mean, you don't have competition. The second one is the cost. So if the cost is tremendously higher, I think that if the cost is similar to the baseline, like a fossil base, customers will be much more open. But if the cost is tremendously higher, it's going to have a huge barrier, right, to the market. So I think those two are the major issues. But in terms of scale, I think you always have to deal with the issues in terms of where to collect those resources and how much it will cost to distribute and consolidate and centralize those resources. If you can't address those issues, it's going to be an issue.
That's true. Yeah. So I think this question certainly is a long-lasting challenge.
Yeah, but there are certain regions. I mean,
Yeah.
you may want to take advantage, right? For example, in a place like, for example, Malaysia, for example, right? It's more centralized and also easy to and more cost effective to collect those resources.
Yeah.
As opposed to some places like, for example, in the U.S., especially in the Midwest, for example, has a huge white land and the population density is much lower. It's going to be an issue.
Yes. Yeah. Okay. So the second question is from the research staff at PolyU, and the question is about how do we evaluate the large amount of energy consumed and we need to produce clean energy, and basically we also consume a lot of energy, and how do we define the role of the catalyst in reducing the energy consumption for production of the new energy? So basically, this trade-off: how much energy input and how much energy it generated.
I don't quite get the question clearly.
So basically,
is the question related to how much energy you need to consider?
So the question is about this: when you prepare your catalyst, and then when you run the catalytic process, like you run 700 or 800 degrees C, and basically you have large amount of energy input, and so just some comments or opinion from your side and how to get this balance.
Well, first, I mean, I'm a chemical engineer by training, right? Every time when you try to convert anything, you have to look at the energy balance. If energy balance doesn't make sense, for example, if you have to introduce more energy than the energy in the product, then you know the answer, right? So absolutely, you have to look at the energy balance.
Yes.
You have to focus on the product, which will have much higher energy than the starting material. Otherwise, it doesn't make any sense.
I think this question may be because when you saw the seminar flyer and because the question comes before your seminar and maybe the audience they guess one thing is about they're talking about the clean energy. For example, if I believe this question is related to something like
no, I think
you produce the solar panel and you put a lot of energy into this, and then how you actually get a good balance in between the energy input and the energy generated by this new technology.
Yeah, now I got it, right? I think especially in today when we talk about green hydrogen or green methanol, for example, right? You really have to assume the energy source, especially hydrogen, where you're getting from. And this is from renewable sources, that's great. But you have to factor in the cost and also the overall efficiency. But I think the positive side is I don't agree with some of the assumptions saying you will get electricity for free, so the energy is free. It's hard for me to imagine you'll get anything for free, because otherwise, who wants to make, who wants to do business in those sectors if the profit margin is zero, right? So would be some cost, but at the same flip side, you also have to look at it. For example, the solar energy, right? The cost, I think, for producing electricity by solar energy is reducing tremendously. So you really can't use whatever numbers, for example, back to 20 years ago, and make assumption. You have to be optimistic. Of course, you cannot be optimistic to the point you feel like everything is free, right? It's going to cost you something. Otherwise, nobody would do it.
Yes, yeah, I completely agree with you. Yeah. So the third question from the list is from the PolyU postgraduate student, and he or she asked the question: what do you think about the main difficulties facing these advanced catalyst materials in moving from the lab and to the large-scale industry application, like cost, reproducibility, or any other effect?
That's really good question, because I don't know any of you actually did any statistical analysis, because that's a question we always face with recruiting students to the chemical engineering field, because most students will ask, what are the chances that I will see the impact of my research or my work, right? Measured by commercialization. And surprisingly, if you look at the entire chemical engineering field, there are only 10% of people, okay, working on the discovery side can see their product eventually being commercialized. And that's really because if you look at traditional chemical engineering field, it takes about 13 years to move from a laboratory discovery to the commercialization, because we're talking about very large scale and very expensive investment. Doesn't matter whether you are looking at a pilot scale testing or eventual commercialization, because those are the $1 billion type investment. Nobody will have the confidence, right, to move from laboratory directly to $1 billion investment without demonstrating, stage by stage. So I think you really have to look at, case by case. For the conventional chemical and the petroleum industries, I think if it goes through conventional ways, that's its reality. It takes 13 years. But you also have to think about what we can do in terms of taking advantage of AI, right? Yeah. Because a lot of data are already available, and a lot of chemical processes, they have a similar type of natures in terms of heat of reaction and the mass transfer, all those characteristics. You don't have to treat each case isolatedly and doing conventional way. So I personally believe AI is a way for large scale, okay? And we have been really lucky with the emission side, because the scale is very small. Whatever you can demonstrate it in the lab, moving from laboratory scale to the commercial scale, right? It's just, 1 to 2 gram powder catalyst to what I illustrated, 5 inches by 5 inches monolith. That's not a huge scaling up. And also another part is a lot of time you don't have the time, because regulation will limit what you have to be, in terms of technology wise. So in those areas, it takes a much shorter process. Yeah. So I think it depends on the nature. In terms of how do we shorten that process, right? In terms of what do you have to be aware of? I'm always a big fan, of very crude techno-economic analysis. Whatever you want to do, you want to commercialize, you have to do a very simple calculation, even like back of the envelope calculations. If even that, very optimistic assumptions, if you don't see it, it makes economic sense, why bother, right? And another part is you always have to take advantage of those TA tools to at least identify which component, which step will give you the big, potential investment return, and focus on those areas.
Yes, Thank you. Thanks a lot. I think this is a wonderful answer. Following question on this list, and which also is relevant to one of the question collected by our team member from online. I believe there are a lot of fans online attending your seminar, and this to the. So could you please indicate the tendency, like the future, and for protecting the catalyst, the activation, like anti coke or anti-loss of metal, and in some harsh reactions like SOFC, for example, Professor Neiman and others working on how to keep them stable and the harsh condition.
That's also a very interesting question, right? Depending on whom you ask.
Yeah.
If you ask this question to a catalyst supplier, they don't want a catalyst, to be stable. Otherwise, they can't make a profit.
They can make money. Yeah.
And at the same time, I think there are some rule of thumbs in terms of meeting certain requirements, right? I think auto catalytic converters is classic example. You can overload catalyst, so which will still meet the performance even towards the full useful life. That's because you have no option. Every year when you send your car for annual, certification, right? You have to meet those requirements. And the autos, like auto, companies could be punished at a very, severe price if you don't meet those regulations. So one way is you just overload the catalyst, but whether that's the best way to do it may not be, right? Another one is, I hope my example today illustrated, you really have to define the boundary conditions. Like for example, every time you develop a catalyst, you really have to look at what are the worst case, conditions that you have to deal with. And you target those, boundary conditions and look at the ways to make a catalyst, which potentially will give you the best chance, right? To be still able to survive under those conditions. Unfortunately, a lot of times we are not as smart, right?
Yeah, I think your like approach, atom trapping is maybe one of the method to lock this single atom catalyst and to be relatively stable, because, and I think I love the words, catalyst is they have the life. When you do the reaction, basically they live moving around. They're very dynamic. So I think it's keep them stable.
I think you made a good point. When we first studied this area 10 years ago, if you look at the literature, I mean, that was like one single atom, like about 13, 14 years ago. The interest in single atom area really, took off. And if you look at the literature, especially the probe reactions, 90% of literatures were using C oxidation, and a lot of research groups were just focusing on a fancy way to make those single atoms and showing, oh, you can oxidize CO at a room temperature or even below room temperature. But the majority of those literatures, never look at how practical those approach, right? And this actually, I think we have benefited tremendously by working with the industries, because they always bring real world challenges to motivate us for the scientific, innovation and also discoveries. And what the first thing we learned from industries is don't, trust any activities before you age the catalyst. They use the term of degraining state. 10 hours, 750 degrees C for, in the presence of 10% of steam. Just treat for 10 hours. Then show us how the activity, will be generated. And we took a completely opposite approach. We want to start with the thermally stable, hydrothermally stable catalysts. We know there are lousy catalysts, but we always had a confidence there must be a way to turn them on and wake them up, right?
Yeah, thank you. And that's very good. I think before I pick up a question from the audience in the room, and the last question from the online audience is quite technical, and this, so in the current emerging technology like hydrogen production using PV plus electrolysis or PEC photoelectrocatalysis, and also the SOFC, like a solid oxide fuel cell based one, and they use a lot of noble metal, like basically catalyst. For example, you already show this catalyst, and so how, and there are some technical questions like how to design the catalyst, from the electro structure design, doping, defects engineering, all these things to stabilize the catalyst and to get a good balance in reducing the noble metal use and still keep the performance.
Yeah, that's I think
it's a very technical. Yeah.
Well, it's not technical. It's really one of the very important tasks catalyst community is facing, right?
Yeah.
Because everyone likes to stay away from platinum group metals for the cost reason, and there have been a lot of approaches explored, right, including forming carbide nitrides or even dopants, for example, and even modifying, for example, carbon support, right? I think it's just like our Chinese way of saying, when the blind people try to touch elephant and trying to tell, precisely what an elephant looks like, really depends on which part of an elephant you are touching, right? I think eventually we'll be able to get a full picture. That's one challenging part. Another challenging part, I think, catalysis community are starting recognizing, especially heterogeneous catalysis community. It's not just a binding site, right? It's not just, for example, metals, but also the surrounding environment, right? It's also important. So it takes, this is well recognized in homogeneous community, because that's one of the important part they're doing is to modify ligands, essentially the environment, right, to tailor the reactivity. So I think a heterogeneous community is recognizing that now. Now you see more people, focusing on beyond the binding site. The third part is also what matters is under reaction conditions.
Yeah.
It's almost like you go to a party. Whatever you saw when the lights are on, right, are different from when the lights are not on. Whatever you saw, when the lights are on, really doesn't represent the real party. And that's also the direction our community in the catalysis area is pushing towards. So with those efforts, I think we should be very positive that we should be able to find a way to identify alternative, right, to platinum group metals. May not happen overnight, but I think the good things will happen.
Yeah. Thank you. I hope the online audience will be satisfied with the Professor Wang's answer here. Thank you. Now, I think we give the opportunity to the audience in the room. Who want to start first? Yeah, please. Maybe you turn on the... Yeah.
Okay. Yeah. Okay, Professor Wang, it's a very honor for me to listen to your lectures. Actually, Professor Wang has done very great work in the heterogeneous, particularly you reported the single atom catalyst. So I'm from City University, but we are also working on catalysis, mainly working on some of the reaction involving water. For example, now we are working on convert sugar to SAF, to long-chain hydrocarbon. So in this case, we use metal-loaded, metal-supported catalyst. But the one challenge which is common for the catalyst community is that how to prevent the metal loss in water environment, because water can leach out the metal. So do you have some good comment or suggestion on how to improve the stability for this metal catalyst in water phase? In water environment?
I think this is also a very good question. It's kind of amazing. I actually started working in biomass area 31 years ago when I first joined the PNL. The effort obviously was trying to do selective hydrogenation in the aqueous phase because by nature, biomass has a lot of water.
Yes.
It makes more sense, right, to take advantage of water environment instead of vaporizing water.
Yes.
Then you have to pay huge energy penalties. But when water is involved, water is really it's really not pleasant to deal with. I mean, for several reasons. I mean, one is just like you mentioned, some of the metals, they actually will be soluble in water environment, right? I don't have a solution, but I always believe you can always turn the problem, into the benefit that you can take advantage. Just think about like one example I shared today, right? All the platinum group metals, they have some volatilities. So if you don't make any, strategic plan, you will eventually lose them. But you can actually take advantage of those volatility to redisperse them on some of the support, which may have actually better interaction with the metal complex. It's not just metal itself. I mean, when water is able to, for example, leach metals, right?
Yeah.
They must form some complex. So I'm positive. I mean, there are some ways to take advantage of those intermediate complex and to put them in the place where they're happier. So you will be able to, solve those problems, just like I shared today.
Yeah, that'd be good. Good. Yeah. Good comment. So how to adjust that. So potential turn those challenges to opportunity to get the water in the water can be also active as a catalyst.
Yeah, or maybe using the way to redistribute metals or reactivate it, right?
Okay.
And I think there are a lot of activities recently in focusing like a so-called self-healing process, right? To increase catalyst stability, for example, or recover it.
Yeah.
If you lose it.
Thank you. That's a very tough question, but I hope we can find a better solution together in the future. Yeah.
Okay,
Thank
thanks
you.
a lot.
Thank you.
Yeah. Any further question from our young fellows sitting in the back? Please.
Good afternoon, Professor Yang. My name is Carolyn. I'm a first year at PolyU studying engineering. I actually graduated from UW last year in psychology, but I switched.
Wrong side of the state of Washington.
Yeah. So yeah, your talk was great, and I found it very interesting. You just mentioned earlier that carrying out clean energy actually takes around 13 years, right? And then
No, I'm talking about the commercializing.
commercializing.
From a lab discovery to the final commercialization.
Okay, got
On
it.
the average, it takes 13 years.
Okay, so considering the fact that Trump has already withdrawn from the Paris Agreement a lot long ago, I just wonder how that's going to affect the research that you're doing, and also essentially, commercializing the findings, and is there like possibility of like diminishing the economic incentives of like companies that are doing the work that you're doing? So I just wonder like your thoughts on this, and not trying to make it too political, but like I want to know the effect. How it's gonna impact.
I think this is also a very good question. In my opinion, our scientific community, right? It's our responsibility and the job to educate non-technical people about why our work is important, right? I mean, if you only emphasize, for example, oh, this process is cleaner and this process is renewable, that's not sufficient. You really have to emphasize also affordability. And that's why I actually use affordable in front of clean energy. If you only emphasize clean energy, if it doesn't make any economic sense, then why do you need to work on, in that area, right? So what I'm trying to share is political side, it doesn't matter. Like, for example, on the current administration, even like for example, the papers we submit, before we submit for publication, we will be requested to scrape out certain sensitive words. At the beginning, a lot of people would have some issues, and it was not easy to accept. But when you think deeply, right, when the general audience read your paper, and if they don't know what clean means, what renewable means, then it's our, responsibility to think, differently. And in the essence, you're not changing the work you're doing. Of course, if it doesn't make economic sense, it will never be, commercialized, will never be compete with other competing, technology. Why do you even, want to work, on those issues, right? My personal opinion is this is not just to myself, but also to my students and to my colleagues. They're saying we also have to convince sponsors to invest in our research. But we have to have the mentality that we believe if we can make breakthroughs in our research, we can, make positive impact. And this research is so important that we even want to use our parents' retirement money for the investment. If you have that mentality, you will choose the right areas to work on, regardless, political influence. Does that make sense? Sorry, it's a long answer.
No, it's very thoughtful, and I think just the words affordable might means like lowering the quality or like the revenue of like commercializing this concept.
No, it's not just about affordability,
Mm-hmm.
right? It also has to be, I think ideally you want to focus on something which is renewable, which is also cleaner,
Yeah.
but also at a cost competitive, conditions. That at least, I mean, maybe initially it's going to be tough, but eventually that should be your goal. And you also have to have the confidence it's achievable,
Mm-hmm.
right?
Thank you. Appreciate it.
Thanks.
Thank you. And in the interest of time, we pick up the last question. Yeah, please.
Professor Wang, thank you so much for your impressive speech. So my question is that because there are quite a lot of research about the selenium-based, oxide-based catalyst and also zeolite-based catalyst for the engine combustions. So my question is how's their performance in a real conditions or real environment, and what is the advantage of each of them? So it's especially for the industry, for the real world applications. Thank you so much.
I think that's, this is going to be a long answer, but I will try to answer very quickly, okay? I think you have to look at it, exhaust, applications differently. For example, stationary ones, like from power plants, right? The temperature is very, stable. And also the conditions are going to be very lean. So there have been a lot of work in using, for example, early transition metal oxides, especially vanadium, modified by moly, those materials. And for example, gasoline engines, which operates at a near stoichiometric conditions, okay? And so far, only the platinum group metal works better. And there have been a lot of work trying to, for example, make the metals more interchangeable, even among like platinum group metals. And also there are a lot of effort trying to reduce the usage of platinum group metals. And there are also, like, for example, diesel exhaust, which is generated under very lean conditions. The temperature will be much lower and the zeolite works much better. But regardless, platinum group metals will be utilized in those applications regardless, because you have to deal with the unburned, for example, hydrocarbons. You also have to deal with the zeolite introduce a problem. For example, when you use zeolite, you're essentially doing ammonia selective, catalytic reduction. Then that would be unburned ammonia. You have to use platinum group metals. So it's not as simple as one catalyst will solve everything. It's if you look individual, applications, it's a very complex system. That's why I started working in this area 10 years ago, and I immediately fall in love with it, because to me, this is like chemical engineering, dream. You essentially are dealing with the chemical plant under, constant unsteady state, but at a much smaller scales. Okay.
Thank you so much for your answers.
Thank you.
Okay, and thank you very much. I believe there are a lot of more questions, and I also equally believe, Professor Wang will answer your question if you send him an email. And
sure, please send him an
very
email.
busy. And with this, we would like to thank Professor Wang again for the very wonderful talk. And so certainly, we learned a lot. I believe there are a lot of opportunities for us to work together in the future. I may invite Professor Chen. You want to say something?
First, we need to thank Professor Wang once more.
Well, thank you all for coming.
To express and pay us appreciation to our distinguished speaker, we make a plaque just for you with your lectures. Professor Wang, and Professor Lau, and Professor Li all together to take another photo. And I also wanted to thank everyone here for your attendance to this distinguished lecture. PAIR organized the distinguished lecture on average about once a month. So you are welcome to attend our future lectures. Just stay tuned for our future announcement. Thank you very much.